Okay, today we're going to be talking about how to multi-thread some of your code so that it runs a lot more efficient on a multi-core CPU or maybe more advanced systems. This is a pretty basic way of doing it, and I kind of laid out the two ways of how you can see, single-threaded work versus multi-threaded work, or at least how we're going to do it. In normal single-threaded work, so like last time when we started talking about writing Hawk scripts to automate things, you have, you fire up Neuron, and from there you have a Hawk script, and you repeat whatever that is across all the parameters you're testing. So that could be, you have like a different environment variable, and you're like trying to test it across a range of that variable, or so for instance, one of them would be like fiber diameter, so you're testing across a range of them and you just repeat it over and over for each one of those, and then theoretically you put all of that output together into a nice single output file. But so the problem is, if your workload, if this Hawk script is very it requires calculations that are based on other calculations. The problem is that's going to run slow inherently because we have to wait for the previous calculation to get done. But then if all we're going to do is repeat the entire thing, why don't we figure out a way to run the other one at the same time? And that's exactly what the multi-threading we have set up does. So theoretically, you could do it all within Hawk. That seems pretty complicated, and with their interoperability with Python, it seems like the Python tools, at least for this instance, are pretty good and are going to be sufficient for what we need to do. So how do we do it to multi-thread our script? And essentially all we do is we have one Python script make a bunch of copies of a other Python script. So we have the master Python script and the child. The child is instantiated by the master, and each child is going to get some set of parameters. And then each child can then fire up Neuron and run the Hawk script with the parameter it was given, and then set some output file. So, and then each one, because they're each going to be running at the same time, this will run a lot faster. Assuming, we don't slow our CPU down by overloading it with tasks. So it's helpful. From what I've seen, Neuron is pretty good at maximizing at least one core of your CPU, and depending on your model, that's going to be a big difference and what all you have set up. But because the models we're using, the MRG model, are all one axon that's pretty long, and all of the compartments kind of rely on the compartments next to each other. That the relying on information from other compartments means it's a bit harder to parallelize it. Theoretically, you could set up MPI and spread portions of the axon across, but for sake of simplicity, we don't really need to go into that depth, because we can get the same idea of multi-threading and getting the most out of our CPU by just spreading the workload of our our main loop. That's one of the things with improving performance is, well, let's see if we can just unroll some of those loops and spread them out. So that is what we're going to do. This is the entirety of what we're going to look like, but we can see it in a diagram, but what does that look like in the code? So I'm going to jump over to Visual Studio Code, okay, in my nice dark theme, and I have two files pulled up: the GNA bar multithread.py and GNA bar experiment.py. And these two are a pretty good example of, they're also a pretty easy example to understand of how to use the master and the child process, and how to instantiate the other, and how to get Neuron running once you're here. So the entire point of this multi-thread file is to instantiate this other one and to give it a set of parameters to run. So that's the entire point of it. So let's go through and we can see how we do that. So obviously there's a couple packages we're going to import, and we'll see what we need them for as we go on. We start off by getting the time, and the main reason is because just to see how long everything took, it's nice to take the time at the beginning, take the time at the end, and at the end we can see how long it took. From there, obviously we're going to need to know where our GNA bar experiment.py file is so that we can instantiate it. And that's what these two lines are going for. They get this folder path, and then they just append the path of the GNA bar experiment.py file. So this is kind of setting us up so that we know what file we need to call. From there, we have a list of processes, and we're gonna store that in a list. From there, we're going to define 5 processes. You might have more, you might have less, and that kind of depends on your CPU and the a number of processes you can keep adding before you max out your CPU. Because once you start maxing out your CPU, the problem is if it's not sufficiently cooled, then it's going to overheat if you're maxing it out, and then it's going to thermal throttle, which means it's going to run slower. So then you have to make sure that you have enough processes that you're putting a sufficient load on the CPU. But if you put too many processes, you're going to be spending way too much time switching between them and overheating the CPU. And so it's kind of a balance of every machine has their own number of processes that it works for. This happens to be a 6-core machine, and it seems like 5 processes works pretty much perfectly. So then the GNA bar, obviously if this is the GNA bar multithread.py file and a GNA bar experiment, our parameter that we're going to be varying is the sodium conductance, and we're going to vary it with some value of 2.7 is our lower bound, and then we're going to do increments of 0.15. And so you can kind of think, okay, we have 5 processes, the lower bound is 2.7, and we're going to do increments of 0.15. It means we're probably going to have one process do testing with the value of 2.7, one's going to test with the value of 2.85, one's going to test with a value of 3, and you can see where it goes. And that's usually a good way of setting it up, is if you know how many processes you're going to do, you can figure out how to nicely divide up your search space so that it's evenly divided across all your processes. So now we have pretty much most of the parameters that we need. They're kind of set up. From there, we're going to, these 4 lines of code are going to go through and instantiate each process. And that's why it's a for loop. We're going to go 1 for each process, and we're going to come up with the argument list. So the argument list is our kind of key for how we're going to pass parameters to the child. So obviously we need to pass whatever the GNA bar value is going to be that's going to test, and so that's what this first calculation does. And then you'll see on the end we just kind of append the procedure or the process value, because that's what we're looping through. So first we iterate this with 0, and then we do 1, and then 2, and then 3, and we're passing that value. And the reason we're going to pass that is because that is how we can index all of our processes. Each process is going to have a different I value, and we can use that as our index to label it. And you'll see later that we need the process ID or that index to be able to differentiate the processes as we go. But we can keep going from here. We use the sub-process package, which is why we need to import it. We need the sub-process package, and then we call the popen method. And the popen method essentially is going to let us have a big list of command line arguments in sequence, and it's just going to basically run that command. And so, for instance, this one we're taking the Python command, and then we take our file path, which is the GNA bar experiment file. So essentially this Python and my file is going to call and run the GNA bar experiment .py file, and then we're going to tack on our list of arguments so that they're going to be passed to this. So this starts the process, and then we're going to append the process to our list of processes. And we're going to repeat this. We're going to create a new process for each different parameter, and we're going to assign it a different index or process ID. And from there, then we can just wait for all of them to get done, and then we can output how long it took. So this does all the work. and all we have to do is make a list of strings that we're going to pass together to the popen method of the subprocess package. So that's the whole master Python script. From there, we can jump over to the child script. And so if you remember looking at that flowchart, the child script is going to need to instantiate neuron, and it's going to then need to start our Hawk script, and then from there it's going to output to a file. And we're actually kind of not doing it in that order in some ways. So first we need to grab those arguments that we passed. And so we have the GNA bar value. We're going to read it from the system arguments, and we're going to grab that process ID. So you need to remember what order you put the arg list together so that you can take it apart. From there, we're going to set up, we grab this folder and we grab my file. And so if you look at this file, we call it file and then processid.csv. And this is going to be our output file. And so we've took the process ID and put it in the name of the file, which means every process we know is going to have a distinct output file. And so you can actually see I have some of them over here in this Python scripts folder. Each one has a different file name, which means we won't have collisions when they're writing to it. From there, the easiest way to set up an output file is to just change the system output for this process. We're going to set it to just write to the file. And that's kind of important because this way we don't have to have our Hawk script writing to a file. It can just write to the console like it normally would. And what we can do is we're just forwarding that from the console to a file. And that's going to save you a lot of time and effort. And it's automatically going to close the file when we're done. So that's very useful. From there, we print at the beginning. So obviously, we can now just use standard print to print to the file, which is really nice. And we can print it. And obviously, if this is a CSV, we're going to do it in comma-separated format. So we can print the GNA bar value, which is the one we're testing, which we got as one of our arguments. And that'll be the first line of the file. Then what we do is we use the neuron package to, this is essentially instantiating neuron for us, for all intents and purposes. And from there, we need to do two things. It's exactly what we need to do when we normally load up neuron, which is we need to load all of our models. And normally we'd set the working directory, but we can also just load up the DLL. And so you just put in the path all the way to the DLL. And then we need to load up the specific file that's going to kick everything off, which if you remember should be the cnow_run.hawk file. So now we've loaded up our instance of neuron essentially that we're using. We've loaded it up. And then all we need to do is pass it the command to start off the Hawk script, which all you need to do is write the method with the parameter value, and we're going to put it all together, and then we just send it to neuron, and it's going to run the command. And that's going to start up the Hawk script, and the Hawk script's automatically going to be writing to a file. And then when all this is done, this ends. When all of the child processes end, we come back here, and we print out how long it took. And that's it. Everything is separated, and the key here is that we're not having the processes talk to each other because they don't need to. And if you can ever separate your workload across different CPUs and across, higher core count machines, having them being able to separate and not have to talk to each other is going to make them run faster because you don't even have to ever worry about them meeting up or doing some sort of message passing or any of that. As long as they're just separate workloads, that's going to be the easiest way. And so that's why setting it up with Python to do these two simple scripts, the fact that it just spreads it out and nothing talks to each other, and then they output to separate files, and then we can figure out how we want to combine the files later. So that is how you multi-thread with Python. Hopefully this was useful, and we'll see you in the next video.